Hello, my name is Frank Wang from the University of Michigan, and today we're going to be taking a look at homomorphic encryption. This lab was developed by Anyi Liu and Xingyi Li from the Oakland University, and supported in part by the National Science Foundation, the Michigan Space Grant Consortium, and the Oakland University. In this PowerPoint, we will go over the learning objectives, the relevant technology, the deliverables, and a point system, and go through a demonstration of homomorphic encryption. We expect that from this lab, you'll be able to use homomorphic operations in both the command line and program level, and be able to solve real-world problems with homomorphic encryption. So, homomorphic encryption is a class of encryption technique that allows for computations to be done on data without revealing what the data is to the server, allowing for total privacy while also using third-party services. In homomorphic encryption, the data is first encrypted, then sent to a third-party server that performs the operations before returning the encrypted answer to be decrypted by the client. There are two types of homomorphic encryption that we'll be looking at today. The first being partial homomorphic encryption, and the second being fully homomorphic encryption. Full homomorphic encryption allows for multiple types of operations to be done to the data, which is usually multiplication and addition in our examples. In partial homomorphic encryption, only one type of computation will be able to be done by the server. This lab will contain 5 deliverables, each worth 8 points. And now we're going to walk through 2 examples, one of a use of homomorphic encryption in the command line, and one of homomorphic encryption through Python programming. These examples will be located in the lab manual, sections 4.1 and 4.2. So here I have a terminal set up with all the necessary dependencies already installed, and we'll go through the lab examples, sections 4.1 and 4.2. The section 4.1 uses a command line utility futil to both encrypt, conduct operations on, and then decrypt a set of data. So first we will use the futil command with the command gen p key to generate the private key of the private key, and we'll set a key size to 1024 and save this private key to private key.json. So we see we have our key pair generated, and we can use the extract to generate a public key based upon the private key. Based upon the private key we just generated, we'll name this one public key.json. So now we have generated our public key, and we can encrypt 2 numbers, still using futil command encrypt. We can output this key into a file named num1.enc, and we'll use the public key to encrypt this. And we'll encrypt a random integer, say 4480. So we've encrypted 4480, and we can do the same with another random integer. Here. So this would all be done on the client side. So the client would encrypt both these numbers and export them off to the server. You can use the concatenate command in Linux to see what num1.enc and num2.enc look like and what the server would be getting, and they would be totally encrypted files with no pattern at all. What the server side would then do is it would perform an operation on this number. So we would use the command addenc to add. Futil commands allow us to both add and multiply the numbers, but in this case we'll add them, and we'll output the sum to sum.enc, and we've added the 2 numbers together, and then This sum.enc would then be shipped back to the client side, where the client would be able to decrypt it using the private key that was set up previously. So we can futil decrypt private key.json sum.enc, the file we're trying to decrypt. And we have decrypted it and gotten 5,900, which is the sum of 4480 and 1420. In addition, the same operations can be conducted using Python, a script. So here I have the fullybasic.py file, which is also located in your lab manual. This is section 4.2. And this uses Python to basically do the same thing done before. So you'll notice first we create the empty Python product object, and we generate the public and private key pair that we did over here in 2 commands. Here we did it in 1. And we've used Python to encrypt 2 integers. In this case, we used 114 and 514. So ultimately, we can take these 2 encrypted integers and both find the sum and find the difference, and then find the multiply them together to find the product, and print the 3, all of which is totally encrypted. So the first section here would be done server side, and the second section here would be done, the first section would be done client side, and the second section would be done server side until the decryption. We can run this file in the terminal here using the command python 3 fully -basic, the name of our command, the name of our file. And we see that we've encrypted the 2 integers before right here, and found a sum which was also encrypted, and decrypted the sum to find the answer. We found the difference also decrypted, and the product also decrypted. So yeah, that's our examples for the homomorphic encryption.